So hello everyone to this first round of the final webinars of IEA Wind Task 51 forecasting for the weather-driven energy system. My name is Gregor Giebel. I'm the operating agent of the task. With me I also have Corinna Merlin, who's the task manager, and Irene Schicker, who will be running the today's edition of this webinar. Today's topic is current status of weather AI, and we're having a program of two presentations, one from ECMWF and one from Met Norway, and Irene will be introducing that a bit more in detail in a moment. We also have a Q&A with Slido. Go to Slido, hashtag IEA 51 webinars, and then you can both put questions there and also upvote those questions so that we, within the hour that we have at our disposal, can get the most important questions first. Since this is a webinar, I would recommend that you close your videos because for the ones that are not talking, it's actually not really needed. Task 51's objective is to encourage improvements in weather prediction, power conversion, and the use of forecasts. And we're having a large collaboration. Actually, this invite went out to some 450 people. So we have large international collaboration between research, of course, meteorologists, forecast providers, and the end users, and have that in 3 different work packages that are somewhat along these lines. We're currently ending our first term, but we're approved for the second term, which will begin in 2022, and that's also the next 2 meetings. One is the final Danish national meeting. If you're from Denmark, please, and want to be there, please let us know. Let me know especially. And then there will be the phase 2 kickoff online from 19 to 21 January 26. And since you're interested in AI weather prediction, there will be a workshop in 2026. Oh, sorry, that's wrong. There will be a workshop in 2026, probably in spring in Paris, 1.5-day public workshop in person along the lines of exactly that topic. And as mentioned, if you want to collaborate or if you also want to be on that mailing list, then please send one of us 3 here a mail. And with that one, I'm getting out of the program and let you take over, Irene.
Yes, thank you, Gregor, for the introduction. And yeah, I want to make it actually quite short as well, because we only have an hour and we have 2, I think, really nice presentations today. And as we all know, AI weather prediction models have really gained attention the last 3 to 4 years, and a lot of models, different types of models, have been generated, have been developed, and are in production. And we have 2 speakers today. We have Rilwan from ECMWF and we have Thomas from Met Norway. And I think I will just hand over to Rilwan for the first presentation. And yeah, the floor is yours.
Okay, yeah. Hi, everyone. I'll be presenting on behalf of AIFS. I'll just share my screen quickly. Can you guys see my screen? All good?
Yes, all good.
Yeah, so yeah, I'll be presenting AIFS and kind of the ecosystem around kind of like yeah, we have and how it's relevant to sort of energy power system sort of things. So okay. So Yeah, so I think in this presentation, I'll roughly cover three sections. First, just the general ecosystem, so different lines of models that we have, which are kind of relevant to this, I guess, this webinar. The second thing would be like a couple of case studies on like extreme events. So a couple on wind, precipitation, and some on heat, and how AFS and IFS fare in predicting those events. And then the third thing is future development. So things which are maybe in production and are close to being sort of made operational, but still undergoing like testing and evaluation. Yeah, so the first thing I'll kind of go into, which will kind of underline the different models I'll present in a bit, are, why we want, like what motivates, um, the use of machine learning for weather forecasting. Um, and I think the first thing I'll start with is it's very feasible to customize these models. And I guess the first of the customizations is they can be very specific for your specific task. So whether it's you're interested on focusing on a certain region or a subset of variables, like maybe ones which are more sort of important to, I guess, energy systems, or even like different features of other variables. So if you want to target extremes for a particular variable like wind, you can do that quite easily. And this is done through like, and usually to do these sort of things, it's usually quite simple, like just change the weighting for your variables or change the data set you're using or oversample certain events. Um, the second sort of useful thing we found, which I'll really show in the sort of second set of the slides, are you get a different error profile to current systems. And part of it, part of that is you're not the operators or the functions you learn are sort of aren't really hand tuned, and I guess there you get different biases. But like the second step is essentially like if like the biases you do learn, maybe you have the scope to reduce essentially the amount of bias or the nature of the bias since you're not sort of following certain steps such as assimilation or normal physical forecasting or post-processing. So you're able to get maybe different error profiles which can be beneficial, may not particularly be better. And the third and final thing, which really does lead to sort of improved speed of model development, is that we're able to leverage a lot of I'd say improvements and um, architecture designs which have been sort of proven to work in other fields of machine learning which are more developed, such as language modeling or video modeling. Um, and like a lot of the sort of developments maybe um, trying a method from that sort of field and adapting it towards weather and trying to sort of push through there. So what you do realize is faster sort of development cycles. Um, yeah, compared to maybe the let's say the IFS cycles, which may take a couple years or on a yearly scale. So yeah, going on to the sort of model suite. I think the first one obviously is operational IFS. So that evolves at 6 hour time steps and generally covers like 13 pressure levels plus the surface variables, which we are increasing. Um, the sort of closely related version of that, which not much changed in terms of architecture. The key thing that has changed is just the model evolves at sort of larger time steps, so daily. And I think, internally we found that, after sort of 2 weeks, this model will have like higher skill in some important variables. But again, like this has shown that this the step from this model to this model, from the operational to our sub-seasonal variant, is literally just changing the time step, which is a very simple change, but has a lot of benefits. I guess the first set of models, which I guess maybe we've spoken about more in the talk after mine, is local area models where we sort of you're focused on a specific region with higher resolution and your model may have higher skill over that region, but it will still be a global model. Um, so yeah, and so like a fourth group of model, I guess you can call it the Earth system variants. These kind of mirror like traditional coupled models. So you can use the same architecture from the AIFS or the sub-seasonal one, and maybe the same way we have emulators and we couple a sea emulator with an atmosphere emulator, you can couple a sort of let's say a sea or sea ice or wave model that uses the sort of ML architecture with the sort of atmosphere version as well. And even as well, we have like one in development where we're sort of modeling, atmospheric gases as well as the normal atmospheric variables. So that's kind of one sort of really great area. And a sort of fifth group, which kind of I guess falls into the idea of what different error profile can we gain by sort of kind of circumventing certain different stages of traditional weather modeling, is a group called direct from observations, where we aim to like forecast and also assimilate from the observations without using reanalysis as our training data, which I'll talk about in a second. And a sixth smaller group is just temporal refinement. So, I mentioned that some of our models evolve at 6 hour or 24-hour time steps. Well, it's often the case that some variables of interest, at these sort of time steps, maybe you'll lose like extremes or peaks. And then I guess the goal would be to like regain those peaks and extremes just for like improved modeling. So I'll quickly just discuss like the model's structure, just so I guess for context. So, in our operational deterministic model and in the ensemble model too, the general format is we take in 2 6 hour like previous time steps of weather state, and then we forecast the next 6 hour evolution. And in terms of like, yeah, I think I mentioned before, we have 13 pressure levels modeled, and an additional set of surface variables, um, including like cloud cover and soil representation. But importantly, how do we train it? So the general structure right now is we'll use a reanalysis, so around 40 years of reanalysis data, using an older IFS cycle, 41R2. Then we'll sort of have a second stage where we try to make the model better at sort of longer range forecasting. So you see right here, up here, I mentioned that, we target the next 6 hours, but, it's kind of great to have a model that can predict up to 3 days or better in advance. So we have a second stage that, tries to focus on that particular goal. And then the third stage of this design is to essentially trying to bring our model or train our model on, you say, a better analysis. So using a more recent IFS cycle as opposed to the like slightly older 41R2. Uh, and then yeah, I'll just go through like some important releases just to kind of give you an idea of like the progress we've made and what we've done. So yeah, AIFS single February 2025. Um, there were some surface variables added, and I think really important, we added some layers which ensured physical correctness. So, previously there was a time when, you know, TP could be negative, so precipitation could be negative, but, added some bounding layers to sort of enforce physical correctness. The ensemble member came out a few months later. And I think the key sort of, improvement you see above the AFS single is you get fields which show better sort of variation. So less smoothing in your forecast fields, which is really important for a lot of variables of interest. Um, a couple of fixes towards AFS single. So I think earlier I mentioned the sort of really I guess the fast development cycle. So updates can be made relatively quickly. It's not maybe the sort of yearly cycle found in the IFS. Um, ERA 6 coming for 2026. I'll go on like in next time I mentioned why this is relevant, but I mentioned that the analysis forms the training data for the current AIFS model. So, any improvements in the analysis or analysis, but should also be reflected in the AIFS model we're able to sort of train and related machine learning models. Um, yeah, the sub-seasonal AIFS variants. So that would be the yeah. I guess this model's also being tested in a web competition called AI Weather Quest, which we have like our model sort of being tested sort of weekly and also compared against other companies and firms that have submitted their model. And yeah, temporal refinement. So, when we release some of these 24-hour models, it'd be great, to also have like diurnal cycles as well. So I think these couple quite nicely. And yeah, so now I'll go into like this case studies, kind of just going over like I guess performance on extreme events. And before I go into explaining like what this diagram means, I think the core message in all these, well, the three charts I'll present aren't to say one model is particularly better or worse, like significantly, but it's more just to show different error profile and if you are coming to like use these models, things to like be aware of and think about. So like what this chart shows is it's kind of showing the forecast skill at different lead times for the IFS and AIFS. And the event is sort of rainfall, so precipitation over 24 hours at Simplon Pass in Switzerland during storm hands. So I'll just get my pen. So yeah, so like what you can see is here you can see like the actual observed rainfall at 17th of April. And what each of these cyan dots and purple dots, I'm sorry, and red dots show is, for example, the cyan is the forecast from the AFS at that particular date. So on the 13th of April, what precipitation was predicted for the 17th of April. So you can get an idea of like when each model sort of starts showing a skillful prediction and what the like how early you can sort of have I guess faith in the prediction of the model for extreme events. So I think the main thing to I think a couple sort of takeaways from this would be if you look at oh, and these sort of horizontal cyan lines represent for this particular sort of point, so Simplon Pass, what is the like basically the average what's the average precipitation value over the past 20 years or 20 or 30 years? So see this sort of horizontal line sort of highlights the 95th percent 99th percentile value for precipitation at this point. So I think the main thing you can kind of see is I guess differences here is maybe they both sort of converge around or they both sort of converge above the 99th percentile, around the 12th of April. So similar behavior here. In terms of which model maybe clearly shows a sort of let's say a raised clear signal, maybe you'd say this cluster of four predictions from the AIFS single is maybe a more clear sort of early signal. Um, but then, when you're getting closer to the date, maybe you could argue that the IFS shows slightly like higher, sort of more correct predictions nearer to the time. Um, and I guess the key thing is you can obviously see this is maybe like just over, well, I guess 10 or so days before the event. Um, do you maybe get a signal of, a extreme event occurring? The next one is a wind event and it's focusing on our ensemble-based models as opposed to the deterministic models. So this event is Storm Floris in Scotland and it's 10-meter winds, also mean 10-meter wind speed. As you can see, the sort of true observation is here. And again, each sort of and for the since it's ensemble models now, as opposed to dots, we have sort of I guess sort of bars that represent the spread and the mean prediction. So within the blue, so for example, this blue one here would be IFS ensemble, and the diamond in the middle is the mean prediction from the ensemble. So I think um again, I think one of the key things is like it's not to say one's particularly better or worse, but I'm more just highlighting sort of behavioral differences. And I think the first thing I want to sort of highlight, which isn't to do with like predictive skill, but it's to do with like nature of our model. You can see that for the AIFS models, which are the ones in sort of pink or red, the compared to the sort of IFS model, um, you tend to get maybe less sort of I guess less spread. So you can kind of see like around Friday the 1st of August, around here, the the IFS is showing like relatively large sort of like I guess spread in the bar in the bar charts in the whisker box chart. Sorry. Whereas the AIFS is relatively more constrained around the same sort of time, and in the days after this. Um, if you were in terms of like determining which one showed more particular sort of skill earlier, you can say that maybe on the 29th of August, the AFS sort of the spread of that prediction maybe has a tail which captures the observation. But in terms of determining which model maybe had a larger spread earlier, you could also say that on the on like earlier on the maybe 23rd, the IFS maybe captured sort of like had an earlier signal of something's going to sort of occur later. Um, and yeah, the next one is just sort of heat events. So I guess trying to cover heat, wind, and rainfall. Um, again, like um, you can see that in this one. You can look at AFS single and um, the true observation being here. AFS single is maybe the first of the sort of AFS single is the cyan and IFS is the red. I mean, maybe AFS single is the first to sort of show a sort of a prediction which maybe indicates an extreme event happening. Um, but then one positive thing you do see is that both the IFS and AFS, like from maybe the fourth or from maybe the fifth onwards, they both present predictions within like a tight window. So I think yeah, again like different behavior. Maybe not one particularly better or worse. Um, and the final sort of slide is just the same event, but using the ensemble models, not the deterministic models. And I think this particular one shows it a tiny bit more sort of shows actually the AFS model presenting a different sort of phenomenon to the IFS. So you can see as both models, so IFS being the blue box whisker charts and AFS being the pink red ones, as both of them approach the final observation, so shorter and shorter lead times, you can see the AFS there's not a compression in the spread of the model compared to IFS. So IFS shows the spread decreasing from the early lead time of 27th of July all the way towards the actual observation date, whereas AFS still maintains an amount of spread which like until the exact very day. So I think this is more just to highlight very different so a significantly different sort of behavior patterns in some senses between the two models. Not to argue one's particularly better or worse at this current point. But the positive is that both models do kind of show like a useful signal. You could possibly argue maybe around the 30th of August when both of their box whisker charts indicate a chance of an event that's over the 99th percentile occurring. Um, and yeah, the final slide. So just covering maybe future developments. For the AFS and the AFS ensemble, one large line of sort of one big push is towards high resolution training. Currently we output on sort of N320 grid, and there's a big push towards getting this towards the 9 kilometer sort of more resolution, and this could definitely help with sort of fields that have um but with which occur on sort of higher scales. Yeah, moving from observations, so using observations more and not relying on the analysis is like one big sort of push. Temporal refinement, I think I've covered earlier. The sub-seasonal AFS ARNs, AFS ensemble model, which, you know, is like largely being evaluated 2 to 6 weeks in advance. Um, one big skip, one big, I know, expected room for improvement should be when the next analysis is developed using the sort of more modern IFS cycle. Coupling our models, so extending the sort of range of parameters it covers. Right now, the AFS is roughly constrained towards atmosphere and land, but adding sea ice, and adding waves are ones that we're really interested in adding. Um, and yeah, using sort of having models which are aware of like the atmospheric gaseous composition is really important. Um, this one's a bit more sort of like I don't know, like yeah, kind of interesting, but like having models which you can essentially also embed anthropogenic sort of changes, so land use changes using geo embeddings, which you may have heard about in a lot of sort of recent geo embedding models, and also models which basically sort of predict direct energy related sort of variables. So this can be like grid load or wind solar production. Um, Thank you for listening to me, and it's been great talking to you guys.
Thank you for the presentation. I would suggest actually that we jump to the next presentation of Thomas and make the questions afterwards. And yeah, Thomas, the floor is yours.
All right, thank you. Can you see my screen?
Yeah.
Also now? Yeah. Okay. So yeah, thanks for inviting me to this this meeting. So yeah, I'm Thomas Nipen. I coordinate the development of Bris, which is Met Norway's data-driven weather model. So we're doing both research on this, but also our goal in the end is to definitely operationalize and this kind of model. Yeah, so here's an outline of today's talk. I'll first show you what this Bris model looks like and how it works. We're going to look a little bit on forecast verification of the model, and then just some comments on our path forward towards operational integration of this model. Yeah, so breeze is basically a Norwegian word for light wind, breeze, like in English, and we're developing this model entirely within the Anemoy framework that Rilwan was just showing. So we're quite fortunate to be able to use an existing framework, and then we just adapt it to our needs, right? So we're our needs is basically high resolution forecasting. We're a national institute, and we need to provide high resolution data. At the moment, we're looking at 2.5 kilometer grid spacing in the products that we provide. And the model we are developing, it's a global model, just like AIFS, except that it has a higher resolution grid over our focus areas, which is the Nordics on the left and the Arctic region, covering Svalbard in particular. So those are sort of our focus areas where we have a higher resolution output, and then the rest of the world is run at a lower resolution. And the goal here is for us to produce a model that we can run seamlessly from basically nowcasting next hour all the way to long range, so the next 3 weeks, with a single model. So this has a lot of advantages compared to how we've done things traditionally with NWP, where we basically have to glue together, often 3 or 4 different models at different time scales to get cover the whole range of time scales. Yeah, basically, the way we're able to do this is because the Anemoy framework is designed around these graph neural networks, which is a very flexible way to define the grid in your model. So we are using this stretch grid approach, which allows us to have 2 resolutions. And you can see here in this example, you can see a lower resolution grid on the left and then a higher resolution regional part. And this model is run seamlessly with both grids. what this with the red and yellow dots show, that's just an example of how the different grid points in our model communicate with the others. So as we're forecasting, the weather moves throughout the globe, and this is how one particular high resolution grid point communicates. You can see that this point has communication with other high resolution points, but it also has connections to sort of upstream information outside the grid. So this works quite differently than typical NWP models that generally only interact with sort of a narrow boundary zone. So that's how we, that's the building blocks that we use in Anemoy. So basically, this is how we adapted the Anemoy framework to work for our needs. So initially we trained some models by using a mean squared error loss function, and we got some good results for a lot of parameters. However, one of the issues, which is definitely true when you move to high resolution, is that the mean squared error loss tends to favor smooth fields. This is sort of a general problem. And you can see here's an example of precipitation. On the left is an NWP, our regional NWP system at 2.5 kilometers, and you can see sort of convection over southern Sweden. And on the right is this data-driven model, and you can see that this model is unable to distinguish between convective showers and sort of large-scale, lighter precipitation area. So, and that's of course a big problem for us as an institute when we need to be able to distinguish between those events. They have quite different impact on the people using the forecast. So we've sort of gone away from training models this way, and we've moved over to an ensemble approach. So basically, this is what the AIFS CRPS ensemble model uses. It basically takes the initial conditions, and then so when you're training a model, you take a set of initial conditions, and then you essentially copy it 4 times. And then you provide it with some noise, some random noise that the model then can use to, however it wants to generate different scenarios. So we don't quite know how it uses this noise, but we know that it does, and it generates then 4 different forecasts. And then you have a truth, right? And then you can use a probabilistic loss function to evaluate these 4 scenarios. So basically, the model will be penalized for not giving enough spread. And so this framing will generally generate fields that are not smooth, like you have with the mean squared error. So here's just an example again. So the top 2 are the figures you saw before, and on the bottom left is what you get if you use the CRPS approach. So the CRPS is what we use in the loss function, so the probabilistic loss function. So you can see that it's getting better. It has some hints of convection, or whatever you want to call it. So it looks better than the mean squared error model, but you can see that it still looks a bit strange, especially there's a lot of noise in the spatial fields there. And the reason for that is that when you train a model against so the way we do it, right, we compute the CRPS in every grid point with no sort of, we're not looking across grid points. So each grid point has a computed value, and then we average all of those. So that score is kind of blind to what happens spatially. And so to improve this, we got inspired by an approach they use at ECMWF, where they try and look at different scales. So you essentially you can evaluate the model at different scales by aggregating them up to the different scales, and then the spread of those scales also has to match the observed, right? So we basically add a few more terms to the probabilistic loss function, where what we ended up doing was to compute the CRPS in spectral space on each wavelength, and so we have a loss function with 300 or 400 terms, right? for the different frequencies. It turns out that this doesn't really slow down the training, so that's not really a big problem, but it will encourage the model to create fields that have frequencies that match the observed, right? And that's where you get in the bottom right figure. So that is the data-driven model with the spectral loss added to it. And you can see now it's getting even better than before. Now you can really see that you don't have this spatial noise anymore. The showers have kind of congregated together and form structures. Of course, I mean, it's not really, there's still a way to go here, because you can see that we don't, some of these features, they look similar to what we have in an NWP model, but they're not. There's still something that's different, especially when you have these sort of elongated stripes of precipitation. That's something we don't really pick up here. But anyway, this is still work in progress. The point of this slide is just to show how important that loss function is, and how it really governs the characteristics of your model. And I think that's especially important at the high resolution. When the resolution is lower, then you don't quite notice these things as much. Yeah, so here's a movie loop of the data-driven model on the left, and the regional, the NWP model we have on the right. So, still differences, but things are getting better. Yeah, I just want to point out this kind of stretch grid approach, right? So we have inside the purple boxes, the model has 2.5 kilometer resolution, and outside it's 31. And you can see how the model kind of represents the same phenomena with 2 different scales. So you have sort of same sort of embedded, like fine scale features that show up in the 2.5, but is sort of more latent in the 31 kilometer. And we can see that we can get these showers show up as systems cross the boundary, even though the resolution is different. So I think that's kind of an interesting an interesting property of these multi-scale models, these models that have different resolutions. So yeah, what we do look at is one of the things we look at is the power spectrum of our field. So how much energy is there at the different wavelengths? And this is, in this figure, is the 0 line is sort of the energy of the NWP system. We're just comparing it to sort of what we're training it against. And so ideally, we like these models to lie around 0. And you can see that the blue line, which is the mean squared error model, has too little energy, right? So it's below the 0 line, has too little energy at anything from 5 kilometers up to several hundred kilometers. There's just not enough energy, and that's we know that because it's smoothed, right? And then the yellow line is the CRPS model without the spectral component. You can see it has way too much noise at the finer scale. And then the green one is this spectral model that is a lot closer to the 0 line. There's still a little bit too much noise on the fine scale. We're trying to figure out how to deal with that, but that's I think we can rely on fixing that eventually. Just some forecast verification of this model. So this is a verification of the model for a 60-hour forecast, verified against station data, so Synop stations in Norway for 1 year. And Bris is the red, and MEPS, the NWP model, is blue. So generally, this model performs quite well, especially on temperature. There's quite a huge. We usually look at these sideways, not vertically. So we see what is the time difference between the lines. So more than 24-hour forecast improvement on temperature. There's not as the same kind of improvement for wind, but we do see some improvements on precipitation and sea level pressure. So this is quite promising that we're able to already sort of compete with state-of-the-art NWP system. These are CRPS values, so these are probabilistic scores. So there's no sort of, not getting any benefit from smoothing or anything. There's sort of no good way to hedge the forecast to improve these scores. So quite promising. Yeah, these are just some reliability diagrams just to show you that in general the models are reliable. I mean, one issue here is that we're verifying against point observations, which don't always have the same characteristics as a grid, like a 2.5 kilometer grid box, right? So it's not going to be perfectly reliable, but anyway, it's not at least on par with the NWP. This is a quantile plot. I just want to show of a single member. I just want to show that we are forecasting the extremes as frequently as we observe, right? So this is, if you're on the diagonal line, you're forecasting an extreme, any kind of event with the same frequency as we observe. You can see our NWP model in black follows that diagonal line quite well. And you can see a deterministically trained, so an MSE-based model, the yellow, it has too little, it doesn't have strong enough precipitation events. Whereas when you train it with an ensemble approach, then you get much closer to that vertical line or diagonal line. It's the same for wind speed on the right. Okay, so this is the last part here. This is about how we are looking to operationalize this. So I think sort of our main goal at the moment is to deliver better public weather forecasts on our weather app YR. So we have a lot of this is the main website used by Norwegians to get weather forecasts, and that's the whole reason. That's sort of the main push here for developing these models. We want models that can give better scale, and of course we have a wide range of users. So there are a lot of products here, time series and maps and all these things. They all have to be of high quality for us to be able to actually use these kind of models in a real life application. But yeah, we're going through all of these products and checking, do we get better? Do the weather symbols end up better? All of the things we have to assess. And here's just some of the sort of roughly speaking what we're looking at in order for us to actually use this model operationally. We're looking at spatial, temporal, and intervariable coherence in the forecast. So the spatial part is important for the maps. They're not important if you're looking up the weather forecast for your city. The spatial coherence doesn't matter. But when we have maps on our website, so we need to look at those, make sure they're good. Temporal coherence is important for the time series. We need time series that look realistic in time. Some of the things we look at are 24-hour accumulated precip and 24-hour max winds. Those are actually values that show up and very prominent in our app. So those are the kind of things we look at to ensure that. I mean, there's one thing is to get accurate 6-hour forecast, but what happens when those are actually accumulated? So those are the things we look at for that. Last one is intervariable coherence. Of course, this is actually really important. If you have precipitation, you generally need cloud. So if you don't have that, then we have a problem. And this is kind of often a problem in sort of classical post-processing, where you might be post-processing precipitation, but then you leave the clouds alone, and then they're not in sync anymore. So I mean, we're sort of used to dealing with this a lot. Same with lightning. You need at least on our app, you need precipitation and clouds in order to put in a lightning symbol. So dealing with these kind of issues or evaluating if the forecast is able to keep these variables in coherent, that's something we look at quite a bit. Yeah, basically we're running this model now operationally, sort of in a test environment in a sense. We're not using the data yet, but we have it up and running. It runs 16 ensemble members 4 times a day on 2 NVIDIA H200 GPUs, which all of this takes 21 minutes. I think if you asked me 5 years ago if you told me that we were running a global weather model with ensemble members in 10 days, all of this basically in the basement of the institute, I wouldn't really believe it. But but here we are. Yeah, these models are extremely computationally efficient. You can run it on, on relatively modest infrastructure. Our future priorities, as Rilwan mentioned, time interpolation is important. We need hourly forecasts, or maybe even sub-hourly. So that's something we're working on quite a bit. We're also looking at how we can integrate real-time observations that we don't have in the analysis that we initialize these models of. And of course, we also would like to extend this work out to 21 days. Then if we do that, then we've sort of covered all the products that we need to serve to the public. And with that, yeah, I'm happy to take any questions.
Thank you so much. Also, thank you again, Rilwan. We do have Slido questions too, but I also see a hand raised. I think. Yeah, Christian raised the hand. Christian, please go ahead.
Yes, thank you, Thomas. Nice presentation. Interesting also to see how you transfer it to the end user. I have used the Euro.no app before. It's nice to have a look behind the scenes.
Yeah.
My question is on the training data set, because you have now two different scales in the model, right? So you need your training data on two different scales as well. So basically you need two different numerical weather models to produce your training or your reanalysis data set. How did you solve this problem?
Yeah, so in-house we have our own analysis at the high resolution, and then we use ERA5 from ECMWF, and then we just train them. So we actually do a pre-training first on the global data because we have 43 years of ERA5. So we do a long training on that to sort of, use everything we can from the whole Earth, and I think that's actually very important here, that because our regional domain only covers 1% of the Earth, and there's so much to learn from the rest of the world. So we pre-train on the whole world, and then we have our 3 years of regional data that we then fine tune on. So that's how we do that. But but getting a hold of these data sets, they're all sort of open data sets that can be you can get a hold of.
And if I may ask, then do you add like layers in your neural network architecture for fine tuning after you have trained on the global data set?
No, it's the same model, just
Okay.
the same. Just we've tuned the learning rate so that we don't forget so it's still the same model. There's nothing in the model that ties anything to a particular grid, because graph neural network is so flexible. You can change the grid, right? You can train on one grid and then train it again on a completely different grid. So we could also train this over Norway and then maybe train it over Switzerland, and then if we wanted to, right? It's the same model and it can be fine-tuned. Yeah.
Okay, thanks.
Okay, then if there are no other hands raised, I'm going to go to the Slido questions, and maybe we just go from top to bottom down, if people are able to vote for the questions. And the first question of Corinna is, what education is required for AIWC in the future? And does the importance of knowledge of meteorology decrease in comparison to math? And I think both of you have quite a different background. So what's your take on this?
Yeah, I guess I'll go first. So yeah, my background is actually machine learning, and my PhD was half in language modeling, so I guess like the chatbots or whatever, and the other half is actually a bit in weather as well. So, and my personal opinion is that so yeah, no, I don't think knowledge of mythology, I don't think the importance decreases, and I'd say especially as these AI models that we're using, or the methods we're using, as they sort of I guess become more mature, like a lot of the methods you would want to use, such as reinforcement learning or these sort of things, like you do need to understand a lot about the nature of the data you're using. And that can range from things such as understanding, the possible sources of bias in different sources of data, or why you may not want to use this satellite over another one, and those sort of things. And you will see some you do see things reflected in your outputs, which being at ECMWF, it's been like great to understand. Like you hear people talk, you hear people explaining certain things and why they happen, and yeah. So from my point of view, it does really matter understanding, the physics and weather, and like a lot of my time has actually just been learning weather, to like go with the machine learning that I already know. That's my opinion on that one.
Yeah, and so my background is I have a PhD in basically meteorology and computer science. This was sort of from before machine learning really took off. Yeah, so I'm more, I guess, on the meteorology side. But I agree. I think you need both in your team. I think you definitely you obviously need the machine learning knowledge to really understand some of these components that are in here. They're quite complex. At the same time, you also need to understand. You also need to be able to know what is a good product. Like when you look at something, someone who sort of worked a lot with weather data can immediately see that, okay, this isn't good, or this is good enough for this application, or here are some problems. So we have quite a diverse team, and I think everything from pure IT, sort of setting up models on hardware, and then and people with meteorology, statistics, and machine learning. So I definitely think you need a mix of everything.
Yeah, domain knowledge does make a lot of sense here as well, and also what the forecasters actually want to use in the end, want to see. The next question is actually by Gregor. How did you spend your summer? And singular vectors or conventional? UPS was also mentioned.
Yeah, I can. So basically, we the way we've done it is that we just, like I was explaining, we give the model a noise field, and then it's up to the model and the neural network to take that noise field and shape whatever perturbations or whatever you want to call it in this framework. So it has enough neural network layers to shape it in something that allows the model to generate different scenarios. So it's sort of a bit of a different approach altogether. We don't fully know how it does it, but as long as when we're developing these, we're kind of trying to give it enough, make sure it has enough complexity that it can learn what it needs to learn, and then we also need to make sure it has the right data. Then we just hope that it does figure out, because the loss function will penalize it if it's not able to create the right spread. Then it will have to go back and retrain itself to use that noise in a smarter way. Yeah, I don't know if you have any to add to that, Rilwan.
No, yeah, I kind of roughly agree. It's quite a large question to answer if you to answer in a lot of depth, but I do agree with the way Thomas explained it. Yeah.
Okay, moving to the next question, and do we need a new way of measuring the quality of weather forecast models that includes the energy used to produce the forecast and the accuracy? That's going a bit towards this green energy of law.
Yeah, I can give my perspective. So for us, the main motivation here is accuracy. So it's nice that it uses less energy, and it has, it's good that we can do this much cheaper. I think for us it's something like 400 times cheaper to run on GPUs, or run this AI model on GPUs than with NUP. So obviously a huge saving, but still the priority for us as a national institute is still to to give the best possible forecast. Now, this might be different for others. I think AI can be a very good way to let you do things that you wouldn't be able to do otherwise because of cost reasons.
But should we quantify also the energy used to produce our training data in the overall energy used for the AI model?
Yeah, I mean, you can add it all up, right? Last time we had a Euro HPC proposal. There we had to calculate how much CO2 emissions we generated from the training of the model. So the training of the models is expensive, but I think it's still relatively cheap to if you're running an ensemble NWP system, for example. But yeah, I mean, these are. I think energy use is can be part of the equation here. How do you looking at that?
And I think both of you mentioned it already on trying to directly use observation data or assimilate observation data into the models. But there are actually two kind of related questions. And do they make use right now of either data directly from wind or solar farms, like SCADA data at hub height, or temperature data from solar farms? And do you think it would add value actually to use this data additionally?
So
Maybe
yeah,
not now, but in the future.
so I can comment on my understanding of that right now. So I can't say they use data from solar farms or wind farms, but for example, they they do use data, like they can use data from observations from like different observational sources. So for example, there's like a weather network from like a company who basically put balloons in the air in the upper atmosphere, and that's recently been ingested into like the ECMWF ability to sort of I guess our data system, so we can use that. This is still sort of being developed, so the source of data which we use and don't use is changing, and I can't say for sure whether or not we would use it, but I think what determines if a data set would add skill to your model is like, one, can it be used as a different evaluation set, which maybe has a high representation of a certain area. Maybe you haven't got some sort of coastal area around Europe you haven't got good observations for. This may be a good alternative. And the second thing is from a more sort of maths point of view, does that data set have relative like low enough covariance with your existing data sets? Like, is there new information in it? And if that's satisfied, then yeah, it would always be good to add more data, in my opinion.
I think another exciting aspect of if you have your own data, like you might have some solar or wind farm data. One thing is to ingest it. The other thing is that you can train a model that directly predicts this from the latent space of the weather model, right? So that might be easier to do than to go from weather to solar. It might actually be useful to just tap into the latent space of these models because that's been that's a very good compressed representation of the atmosphere, and you might be able to train with a lighter neural network, a separate, in a sense, a decoder, or like a post processor, what you want to call it, that then directly predicts what your interest is if you have your own data. So I think that's an interesting, also an avenue in the future where special data can be used in some kind of way.
And I think we have time for one or two more questions. And David asked why the random noise was added to the initial conditions, and if maybe using predefined patterns such as discrete cosine transformation would be an option or would be better than just random noise.
Yeah. So we've only, so at Menro we've only looked at the noise. But yeah, you could probably, I mean, that is something that could be interesting to test some other type of pre-processed noise that has certain patterns or whatever, if we don't think that the model itself can figure these out. We're kind of hoping that if there is a better noise structure, that the model has the complexity to learn what perturbations give you a good ensemble several going forward in time. But I think there's a lot of interesting work that can be done on the perturbation side, or on this generative side of this model.
Can I answer one question as well? So there's quite a few questions which similar to the question just asked, which kind of ask about maybe choices that I've made and is this the best way, and like what are the advantages of changing certain things. Like one thing I would say is that this is all like really new work, and there are a lot of areas that definitely can be improved on, which usually are based on people having intuition based on their knowledge of weather, on what should be changed, what should be improved. And I would say that there are a lot of things which could be improved. Like nothing's like the choices which are made in the model right now. Some of them have just been made because you need to start somewhere. So a lot of the suggestions can also be, a lot of the questions can also be answered by this is how we've done it now, but there's definitely room for improvement. And if you have a good idea, please do download the Adewoyin repo, run it yourself, go Hugging Face and say, look, this works really great. We'd really appreciate that.
Yeah, I think these were quite some nice famous last words for a webinar. And looking at the numbers of participants dropping, I would suggest to stop for now. And I'm just stopping also the screen. And thank you both for giving the presentations today, for the nice discussions, and I'm really looking forward to see more, and also looking into more detail into how the models perform for energy related directed forecasts. And thank you again, and wish you all a nice evening.
Thank you. Bye.
Okay, thanks.
Thank you.
Yeah, we try maybe to let the two answer the questions and send it out to the list. So those that have not been answered, so we'll try to get them answered. Bye-bye.
Bye.
Bye.